controlling the climate, refreezing the Arctic, there are two projects really that I've been involved with. One is the Spice Project, and the sugar goes with spice. The alternative name for sugar is spring. The acronyms for those are stratospheric particle injection for climate engineering, solar updraft, greenhouse gas removal, or solar photocatalytic removal of non-CO2 greenhouse gases. And I'll be talking about these as we go. The first thing is just by way of introduction is to say that this is how CO2 has been varying for the last almost 1 million years, up and down, up and down, up and down, various ice ages. This is where the last ice age was. This is the last 4,000 years or so when we've been able to develop as human beings, and this is the CO2 level right now. So things are rather different, and they're dramatically different, and they're changing in a way that hasn't changed for 1 million years. If we look at temperature, what we'll notice this is temperature since 1880, and the temperature, this is 0 degrees as a reference, 1 degree above, it's been rising up and up and up. This is the so-called pause, where temperature wasn't changing, therefore everyone was saying that climate change wasn't happening, and this is where we are now. So these, I'll try and explain terminology as I go. Anomaly is used a lot, and it simply means the current value minus some reference value, which is fair enough. But now let's look at non-CO2 greenhouse gases, because CO2 is not the only greenhouse gas of interest. So this is the last 2,000 years, and you'll see that the CO2 levels have been fairly steady up until recent times. The methane levels have been steady, and they started rising. Nitrous oxide rising as well. You might notice that CO2 is measured in parts per million, but nitrous oxide and methane are measured in parts per billion. So they're much less, there's much less of those gases, but they're much more potent. The temperature rise, if we look at the last 130 years or so, that's just this band here, expanded out, and look at it month by month, you can see again this kind of colour coding. Redder means hotter. It really is very visible that things are changing. Now, if we look at that more closely, this is decade by decade. So here we are in 1892 to 1896, so that's 5 years at the beginning of the 1890s. Colour-coded again. The anomaly, the reference baseline is the average over the period 1951 to 1980, and the white is no change. Blues are colder, reds are warmer. So you can see as a snapshot, there will always be, at a given instant, periods where things are warmer and things are colder in various places. Now, we're going through a decade at a time, so you can see the years changing here. And it says hot spots and cool spots, half a degree here, a half a degree there, but it's only when we get to, I'll skip 2 years there, it's only when we get to the recent decades that we really notice that the Arctic is getting hot. So just going backwards, that's from the 1980s, 1990s, the 2000s, 2010s, that's where we are now. So the worry is that the Arctic is getting hot, but is the Arctic going to melt? So this is quite a nice graphic which helps to visualize this. Now this is from 1980 to, well, this is where we are now. And this is in ice, the quantity of ice in cubic kilometers in the Arctic. This is sea ice, floating sea ice. So typically in midwinter, there has been of the order of 30,000 cubic kilometers of sea ice. And during the spring, summer, the melt, the amount that melts is of the order of 15,000 cubic kilometers. So you can sense that the maximum you get in winter minus the minimum amount of ice in the summer is the change. So here's the change, and it was fairly steady for a while, but the change has been getting bigger, and the maximum has been getting smaller. These are measurements, satellite measurements. And it's relatively easy to extrapolate these two curves with, I don't know, how much confidence, who knows. But this is the worrying thing, that it's quite possible that in the next 5 or so years these two curves intersect. And once we lose the summer ice, then, well, what happens? The albedo, the reflectiveness of ice, is about 6 times greater, and that's 0.6 compared with 0.1 of open water. So we then get a warming effect simply because we're not reflecting as much sunlight. And that's estimated to be equivalent to about the past 25 years of CO2 emissions. The Arctic Ocean is shallow. Surface warming will then extend down to the sea floor, where there's permafrost, which has been frozen for a very long time, and in the permafrost is locked up methane. Now, we don't know whether the methane will be released. It's speculation, but the worry is that if it is released, we know that methane is a substantially more potent greenhouse gas than CO2. So that's a worry. And then if we then start getting warming of the Arctic region more than we're getting now, we know that the Greenland ice shelf holds 2 million cubic kilometres of ice, which is on land, and if it melts, that will account for about a 7-metre sea level rise. And the ice-free Arctic will change jet stream patterns, and it will change ocean circulations, which will lead to quite dramatic changes in climate. But we don't know we don't have a crystal ball, but as engineers, what we do like to do is to at least to know what the current concerns are, so we're at least forewarned and perhaps prepared. The SPICE project that I was involved with, part of it, one of our partners was the Met Office, and they ran climate models for the effect of the changes in temperature around the planet with and without geoengineering, which I'll come to shortly. But without geoengineering, it's called business as usual, BAU. This is 90 degrees south, so this line represents the Antarctic, this represents the Arctic, here's the equator, and you can see familiar shapes, they're the various continents. And in 2090, the modelling suggests that, well, you can see it's going to be quite warm in the Arctic, perhaps 20 degrees warmer, 8 degrees warmer in North America, Amazon 8 degrees warmer. Well, we're talking right now of hoping to limit temperature change to 2 degrees, perhaps 1.5 degrees. Well, we really have to work on that. Now, these are computer models, and the computer models are only as good as computer models can be. And they're getting better all the time, but again, we don't have a crystal ball. This might happen, it might be worse, we just don't know. So this, what about the future? Here we have 1900, 2000, that's where we are now, 2100, 200, 300. This is kind of a guess of what business as usual might be. And it's as well to know some of the terminology because it helps when you're reading stuff. There are these things called RCP 8.5, RCP 4.5, and they're kind of meaningless things unless you know what it means. Representative Concentration Pathway, Intergovernmental Panel on Climate Change uses this terminology, and RCP 8.5 means that in the year 2100 there will be 8.5 watts per square metre greater heat getting to the surface of the Earth than there was pre-industrial. And now the solar constant out in space near the Earth is about 1.3 kilowatts. So, and maybe half of that gets to the surface of the Earth, it depends on where you are. The 8.5 watts per square metre it's a smallish number, but it's having a big effect on the imbalance of the temperature of the Earth. So the idea then is that if we want to stay below 2 degrees, the thought is we have to follow RCP 2.6, which means that we have to somehow reflect or somehow deflect 6 watts per square metre of solar radiation. There we go, and if we fail to do that, well then we might be 3 degrees above pre-industrial. That's still RCP 4.5. Alright, let's have a think. This is our CO2, these are our CO2 emissions globally per year, 1850 now-ish. We're currently generating about 35 billion tonnes a year of CO2. Global population is 7 billion. Divide one by the other, the global average CO2 production is about 5 tonnes per person per year. Now I was trying to estimate how much garbage we generate at home from the kitchen, and I think probably I could, if I really pushed my estimate to its upper bound, I could say that I personally am responsible for maybe 500 kilograms of rubbish per year. I sort of doubt it, but let's assume that I'm worse than I think I am. My kitchen refuse, personal kitchen refuse, is 1/10 of the global average CO2 refuse. But worse still is that if I go to Australia to see my family, one return flight to Australia, my share of the CO2 on the flight is 5 tonnes. And it's not a difficult calculation to do, and it's really hard to see how can it be that big. Well, you're on a plane, and you arrive at your destination, and you pick up your 20 kilogram suitcase, and you think, well, supposing I had to pick up a 20 kilogram suitcase which contained dry ice, my share of the CO2. Well, how many of those suitcases do I have to pick up? The first thing you do is you look up on Wikipedia or wherever you want to look up that your plane burns fuel at certain rates, and that the flight is 20 hours, and there's 350 passengers, and that each kilogram of fuel generates 3 kilograms of CO2 because of the chemistry of carbon combining with oxygen. And you do the sum, and you discover that I ought to be picking up 125 suitcases of CO2, each weighing 20 kilograms, when I arrive at Sydney Airport. And I probably ought to do what I meant to do in the kitchen, which is to clean up my waste before I go to bed. So, I should, before I check into my hotel, deal with my 2.5 tonnes of CO2 waste. But I don't, because I just pick up my suitcase and I go and enjoy time with the family. And of course there's the return flight, which is another 2.5 tonnes. The rule of thumb is when you're flying, you're generating about 100 kilograms of CO2 per hour of flying. So you're sitting in the plane, minding your own business. A house brick weighs 2 kilograms. For every hour, you've got 50 house bricks landing on your lap. And your neighbour's got 50 house bricks. Everybody in the plane has got 50 house bricks landing on their lap. So after 10 hours of flying, you've got 500 house bricks. So forget deep vein thrombosis, your legs are going to be pretty sore from the house bricks. But you've got to dispose of them. Anyway, we don't know about this. Okay, so what are we going to do? Here is our emissions. It's been growing and growing and growing, and nothing seems to have slowed things down. We've got to come back down here to prevent that, to bring that RCP 8.5 down to RCP 2.6. That'd be great. And it seems that geoengineering is what we need to do. And geoengineering is active control of the climate in some way. Now, let's think of what geoengineering proposals there are out there. There are some pretty wacky ones, like putting space reflectors in orbit around the Earth, or various ideas. But the most common ones, just about everything has a 3-letter acronym. There's solar radiation management, carbon dioxide removal, and this one, bioenergy with carbon capture and storage. there's a lot of faith being put in bioenergy with carbon capture and storage. The idea is you grow trees, and then you burn the trees, but you capture the CO2 from the stack, the chimneys of the power station, and then you put the CO2 somewhere safe underground. Well, we're talking about 35 billion tonnes of CO2 that we're generating at the moment. So that gives you an order of magnitude of how much of this bioenergy and carbon capture and storage we have to do. We're talking about billions of tonnes of trees per year. We really need to do it, but if we're talking about the Arctic melting in the next 5 or 10 years, maybe we won't have that ready in time. So other carbon dioxide removal techniques, which also probably won't be ready in time, we can fertilise the oceans so that we can increase the population of algae and just sea life. Seaweed will absorb CO2 just like trees do. And then we can perhaps growing trees, just full stop, is a good idea. That absorbs CO2. But when the tree's fully grown, we can't burn it. What we have to do is to do what's called biochar, which is you heat the tree up so that it forms charcoal, and then you bury the charcoal, kind of put the charcoal back into the coal mine where you got the coal out of. It seems a bit silly. Then all these solar radiation management techniques, we could make clouds more reflective, spraying sea salt into them. It's an interesting idea. It has the potential to work, but again, it's at early stage of thinking. We can increase the reflectivity to the oceans. If you make the oceans a bit more foamy, so when you can imagine putting something into the oceans that just makes them a little bit, the oceans a bit whiter. Well, that's a good idea. The increased reflectivity from deserts, so we could sprinkle white crystal, nice white powder on the deserts. Well, that's a good idea. But all of these are just a bit. We don't understand what the effects of them will be on the environment. The one that I've been looking at is putting particles in the stratosphere, and we certainly don't understand fully what the effects that would be on the environment. So before we do any of these things, a lot of work has to be done. IAGP was a project funded at the same time as the SPICE project, funded by the EPSRC and NERC. So where we're at really is that the COP21 Paris Agreement has implicitly legitimised geoengineering because we have to reach a 2 degree or preferably 1.5 degree, we have to not exceed 2 degrees temperature rise. But implicitly it's relying on BECCS, bioenergy with carbon capture and storage, as a technology which will enable us to do this. Technology doesn't exist yet, at least not at a scale that can be used to get us to that target of 2 degrees. I like this photo. I was there in Paris and they actually had a tethered balloon up there, so I was quite pleased that they were doing a little bit of tethered balloon research. Right, now let's go back to this graph. Here are RCPs. This is just the next 90 years. And we're not going to do anything straight away with geoengineering. It's going to take us a while to get settled. And perhaps if we start carbon dioxide removal, there's a moderate amount of it, a large amount of it. Well, they're the different RCPs. So RCP 2.6, the one that's going to limit us to 2 degrees, is a large amount of carbon dioxide removal. And all the modelers will tell you that. Why it is not written into the Paris Agreement is a bit of a con, if you ask me, but there we go. So, Can we meet our 2-degree threshold? I don't think we can do it with our present thinking just on carbon dioxide removal. Emissions reduction doesn't seem to be working at all because we're building more runways rather than closing them. We're making airfares cheaper rather than more expensive, all these things. So solar radiation management, the SPICE project involved emulating the effect of volcanic eruptions. This is Mt Pinatubo in 1991. And it's not all this mucky brown rock and dust and crappy stuff that we're interested in. We're interested in the volatile stuff that makes its way right up high, 20, 30 kilometers up. And it affects the optics of the upper atmosphere. This is a picture taken in 1984 and a picture taken from the same place in 1991, just after Pinatubo erupted. So there's obviously something happening in the atmosphere. Well, it turned out that in 1984, there was this satellite that was launched with an Earth radiation budget sensor on it. And so the satellite goes around at a 57-degree orbit, and the Earth rotates underneath the satellite. So you scan the whole Earth once a day, which is great, or twice a day. So this is what's a measurement of what's called optical depth at a wavelength of 1020 nanometers. It's just an example of the data which is available about Mt Pinatubo's eruption, and it shows immediately after the eruption, a couple of months later, a couple of months after that, and then this is a couple of years later. So this is the normal optical depth, and this is what happened after Pinatubo. So a lot is known about Mt Pinatubo, which gives us confidence to think that we could use sulfate, or use aerosols in the stratosphere like Mt Pinatubo's eruption to cool the planet. So within the SPICE project, the Met Office said, right, there's that business as usual graph that we saw before. Can we model the effect of putting aerosols into the stratosphere and see whether by 2090, with geoengineering solar radiation management, we can make things better? And the answer is, well, according to the computer models, yes. But we can't just have one person run one computer model and say, oh, good, right, we're all sorted. A lot of research has got to be done to check and check again and to see what there's so many things we don't understand. One thing that we did in SPICE was to look at precipitation. This is precipitation change. Blue is wetter and red is drier. By 2090 for business as usual. And, well, sadly, solar radiation management doesn't really help us out, particularly in equatorial regions, on precipitation. Equatorial regions are going to dry up, whatever we do. It doesn't also help us with ocean acidification, because the CO2 will still be there, and the oceans getting more acid is a problem. So, but let's suppose we're going to do solar radiation management. We've got to think, how much stuff do we need to put up there? Well, we know that 10 million tonnes was about what Pinatubo did, and it caused sort of a half a degree cooling. So if we put 10 million tonnes of stuff up every year, and we keep on doing it in steady state, we reckon we can get a 2-degree cooling, and we have to get it up to about 20 kilometres. So how might we get the stuff up there? Well, there are people saying we can use aircraft, but the aircraft that are available now to get up to 20 kilometres have a payload of about a tonne, so we need about 30,000 flights a day if we use present-day aircraft. So we have to design new special aircraft if this is going to be feasible. So we better get on with it if we're going to do it that way. Missiles, well, I mean, missiles are even worse. We have an awful lot of missiles. Chris Burgoyne has a great idea that we should build a tower, which is... No, sorry, Chris, I shouldn't do that. Let me rephrase that.
My idea.
Chris Burgoyne has analysed the absurdity of building a tower that's 20 kilometres high. Just for reference, here's the height of the Burj Khalifa. So it's pretty unlikely that that will be a viable solution. many of you will know that we're looking at, for the SPICE project, at the feasibility of tethered balloons. The advantage of this is that it's possible, if it can be made to work, to do the 2-degree cooling with perhaps only 10 tethered balloons around the Earth. So it's kind of like watering your garden. If watering your garden with a hose, you can put the hose out, put it on the stick, go in and have a cup of tea, an hour later move the hose. Whereas if you have to water the whole garden with buckets, you're at it all the time. So we kind of thought we ought to explore the possibility of tethered balloons, because if they can be developed, they can be developed quite quickly and possibly quite cheaply. The Richard Towers thing here, I think, probably ought not to be on there at all, because I think it's an impossibility rather than a long time scale and expensive. So here are the aircraft. It's probable that the aircraft will work. And if you think that a nuclear power station costs of the order of £10 billion, it's all affordable. It's not that we can't use aircraft, but tethered balloons might turn out to be easier and better. Our SPICE project was deemed to be very controversial, and we weren't allowed to do any outdoor experiments. And that was in 2012. Here we are now in 2017. The SCOPEX project in Harvard has just been announced, and they're planning to do some experiments with 10 kilograms of water to start with at 20 kilometres, and perhaps then 10 kilograms of calcium carbonate. So 10 kilograms is a start, but we've got to get to 10 million tonnes. So, are we going to get this done in time? Well, perhaps, but we've really got to be working on it. Carbon capture and storage, well, it's the scale of it. If you think of 35 billion tonnes of CO2, well, that's 1 million kilograms per second of CO2. It's 2 cubic kilometres of CO2 per hour. So if you think globally, 2 cubic kilometres of CO2 is what we're producing. If we disperse that in the air at 400 parts per million, and then we want to extract it again later, well, rough sum, we have to handle a cubic kilometre of air per second, and these air extraction systems are being proposed. Well, handling a cubic kilometre of air per second is, well, cubic kilometre. Cambridge, 10 kilometres this way, 10 kilometres this way, 10 metres high, that's a cubic kilometre of air. So if you want to take out all of the CO2 that's in that volume, do that every second. That's the scale of what we have to do to extract 35 billion tonnes of CO2 per year. We've got to do it, but it's unlikely that we're going to do it in the next 5 years. We've got to do it because of ocean acidification, we've got to do it for all sorts of reasons. But in the meantime, the Arctic is melting. So what we've been thinking about as part of the sugar project is photocatalytic removal of non-CO2 greenhouse gases. So this is really worth understanding what's meant by GWP, global warming potential, subscript 100. Means 100 years. Actually, I'm doing subscript 20 here, which means 20, so that's a typo. I have to fix that. Global warming potential 20 means that in 20 years, methane will have 86 times as much effect in the atmosphere than will CO2. Nitrous oxide, 268 times as much. CFC12 is one of the greenhouse gases, one of the refrigerants responsible for destroying the ozone layer, is 10,000 times more potent than CO2. But look at the concentrations: CO2 400 parts per million, methane 1.8, nitrous oxide 0.3, CFC12 0.005. So you kind of multiply this by this to get a figure of how much air do I have to handle every second. It's a cubic kilometre for CO2, 7 cubic kilometres per second for methane, 4.5 cubic kilometres for nitrous oxide. But it does make you think we're in the ballpark that if I find it difficult to remove and sequester CO2, maybe it's not madness to remove and sequester nitrous oxide? Well, especially important since nitrous oxide and methane are on the rise, and if the Arctic melts and permafrost starts doing its job, then maybe methane will be moving up to the top of the league table. We don't know, but it's perhaps worth getting the infrastructure in place. Now, what is key is that we can do what's called photocatalysis, take methane, burn it with oxygen, but at really low concentrations, you can't just set a match to it. I don't set a match and the 1 part per million of methane in this room suddenly ignites. No, because it's below the flammability limit. But if you have a catalyst around, then it will happen with UV light. And look, it goes to a gas. Okay, CO2 is a greenhouse gas, but it's 1/80th as potent. Same with nitrous oxide. It goes to a gas. So gas to gas conversion, no need for sequestration. So that leads us to our spring project, or sugar, solar updraft greenhouse gas removal. And a solar updraft tower, very fairly popular concept in the 80s. This one was built in Spain. You have a large area of greenhouse, that's what it looks like underneath. And underneath the air gets really hot. Hot air rises up the chimney, and you put a wind turbine at the base of the chimney to generate electricity. And they did that in the 1980s, and it was very clever idea, but along comes solar photovoltaics, and that turns out to be it's kind of easier, and it's the flavour of the month now. But there are possible solar towers being built, and what you do is you perhaps plastic or glass, whatever you use up here, you coat the underside of that glass or plastic with a thin layer catalyst, and UV light from sunlight converts methane and nitrous oxide to other gases. So let's do the sums on it, and I've got a spreadsheet on this if you want. You can send it to you. Suppose we have a tower height of 800 metres. You can do that, Chris, can't you? Have a tower height of 800 metres, diameter 100 metres. These perhaps might be made with some kind of tensegrity fabric structure, so that it's not a rigid structure. If we wanted to remove all the methane and all the nitrous oxide that is in the air that comes through this tower, we want to have the effect of 35 billion tonnes of CO2 removal, then we need 4,500 of these towers. The diameter of the collector is, from there to there, is 8.5 kilometres. The total land area of all of these things is about 40% of the area of France. But of course it's in the desert. And the deserts are okay, because we sort of think, okay, we're in an emergency situation. We can put them in the desert because there's no power supply required, no electricity required for this, no pipes required to take the CO2 away, no, it just runs. And maybe because the glass required for this greenhouse, glass is made of sand. So if glass is made of sand, where might be a good place to put the factory that makes the glass? Here. So it kind of might make sense. And I don't know if it will make sense. There's all sorts of questions. We've got questions about, well, okay, what if we extract all this nitrous oxide from the atmosphere? What effect will it have on the climate? What happens if there's lots of nitrous oxide dissolved in the oceans? And maybe if we go to the trouble of taking it all out, the oceans will just put it back in again. People say that water is a greenhouse gas, so why don't we get rid of all the water in the atmosphere? Well, of course the oceans will just put it back in again. So Parv here from University of East Anglia works on just this sort of thing. So if we're successful in getting this project done, that's one of the questions that Parv's interested in. There are other questions which are really important, like nitrous oxide. Well, aren't those NOx emissions from your car really nasty? Well, yes, NO2 is the nasty one, that's right.
Which one's the nasty one? So this is N2O. But what if we accidentally create lots of NO2? You know, we've got to be really careful, and that's why this is a great research project which covers lots of disciplines. Last slide. So, can we refreeze the Arctic? Yes, I think we can. That's what the SPICE project is about. Should we refreeze the Arctic? Well, in my opinion, I think we should, because if we don't, I bet you our grandchildren, great-grandchildren will say, well, why didn't we? Will we refreeze the Arctic? No, we won't, because we won't get the regulatory frameworks in place even to do research, let alone to implement this geoengineering. And if the Arctic melts, can we deal with the rise of methane? Well, maybe we can, and that's what this sugar solar updraft greenhouse gas removal project is all about. And if we don't get around to refreezing the Arctic, can we handle sea level rise? Well, that's beyond the scope of this talk. So what I've done is I've kind of stuck more or less to the time in our tea time talk people would expect to be going. But I wanted now, anyone who wants to go, most welcome to go, no problems with that. But I wanted to have a discussion, because we've got lots of people who are here who are interested in taking this as a subject further. So thank you very much for coming, and if you do want to leave now, by all means, leave. Great, thank you very much.